fan of programming languages for a long time, especially functional programming languages. I learned about Scheme at BYU ages ago, and just the idea of maximum continuation were mind-blowing at the time, and they're still kind of mind-blowing, really. But that's led me through a lot of different programming languages, and I won't say that Haskell is the last programming language. It's probably the final word in functional programming, but it has a unique perspective that isn't found in a lot of other programming languages today. So really, what is the essence of functional programming? Well, we'd like to think of a function as sort of like the mathematical concept of a function. You have a set of possible inputs, and they are mapped to a set of possible outputs. Nothing else happens. It's just a map from inputs to outputs. That's very different from your standard imperative programming idea of a function, where you have some things that it accepts and some things that it returns, but it can do anything it wants while it's running. So the idea of functional programming is that programs are built mainly from functions rather than from statements. And the functions are first class in the language, meaning that you can treat a function like any other piece of data. You can pass it to another function, you can return it from a function, and this allows, or really demands, a very different way of thinking about programming. So, one of the big things in functional programming is that you don't have side effects. You can't print to the screen in the middle of a function, because that's not what a function does. A function maps from inputs to outputs. If you print to the screen in the middle, it's a procedure. It's not a function. In a purely functional language, the order that things are evaluated, if all functions are just maps from inputs to outputs, it doesn't really matter in which order you do the mapping, as long as it reduces down to the same value in the end. So the order of evaluation is less significant than it is in an imperative programming language, which really is defined as a sequence of statements that occur one after another. And really, to program in a procedural language, you have to think about the order of the way things are occurring. And another big thing about functional languages is that you can reason with them like you do with mathematical functions. So who here remembers high school algebra? So yeah, think about functions the way you learned what functions were in high school algebra. It's very different from the way you think of functions as a programmer, at least if you were brought up with imperative languages. But a lot of what you do in algebra is symbolic manipulation of equations. You learn a whole bunch of rules that let you, it tells you what kinds of things you can do to an equation to manipulate it into a form that's nicer for you to use for whatever reason. And Haskell is really, at its core, designed to allow you to use the kind of reasoning that you do in your high school algebra class to solve problems. So, I mean, you ask people what's important about functional programming, and you'll get a lot of different answers. Some of them will say, well, the point is you can't to side effects, or you can't assign variables. And those can be helpful, but they don't actually increase the power of a programming language. They let you reason about it better, but you don't necessarily get any more power out of it. The thing that makes functional languages more powerful is providing better tools for abstraction. And by abstraction, I mean moving away from the details of a problem in a way that lets you still solve the same set of problems, but without getting down to the low-level details of the steps that you have to go through to solve. And functional programming and Haskell in particular provide more tools for making your programs modular, for dividing them into pieces that you can put back together in new and interesting ways. So the way that you do, or that you get this modularity in functional programming is through higher order functions. And by that, we just mean functions that can be passed to or returned from other functions. This lets you define sort of a general strategy for solving a problem in one function, and supply it the specifics of how to solve that problem for a particular kind of sub-problem as a parameter. So you can build data structures that describe the structure of your problem domain, and you can define general functions that solve the general class of problems over those data structures. And then you can write the specific kind of function for the problem that you want to solve with respect to that data structure. So basically what I mean is that some problems are sequential. You have a series of things and you want to do something to all of them. Well, there's a function you can write that will visit each member of that sequence, and you can pass it another function that will operate on each member of that sequence. There's another one that will operate on all of them and sort of reduce them to a single value. But you have to supply a higher order function to give that general idea of summarizing a list. You have to tell it how to summarize it. And the thing about functions, and this is goes back to mathematical thinking, is that functions are compositional. If you have a function that takes one type as input and another type as output, and then you have a second function that takes the output type as its input, you can stick them together. And you don't have to worry about there being some conflicts behind the scenes, because functions just map one type to another. And as long as the types that the functions operate on are compatible, the output of one hooks up to the input of another, then you can hook them together. So the really unique thing about Haskell is the way that it evaluates functions. So Haskell has an evaluation model that's known as LAZY, which means basically that it doesn't compute the value of a function until it's asked for. And this allows you to achieve more natural interleaving of processing between functions that build data structures and functions that consume them. It gives you the ability to do amortized cost data structures, which if you've taken algorithm analysis, there's big O notation that gives you the upper bound on the amount of time that it takes to process an algorithm. And they generally give you the worst case. Functional programming tends to have worse cases than other approaches to solving algorithms. But there are different ways to approach building data structures that you can do a bunch of work up front and then pay it off later and end up with what they call an amortized cost that's more reasonable than you might think it would be with the standard analysis techniques. And that's not really giving the topic justice, but I don't know the terminology well enough to really get into it. Anyway, lazy evaluation is a key part of functional data structures that are efficient. It doesn't require that you do lazy evaluation by default like Haskell does, but you need to at least be able to do it. One other thing about lazy evaluation by default, and probably the thing that has most shaped the way that Haskell has evolved as a language, is that lazy evaluation means that it's difficult to see when you look at your program in what order your functions are going to be evaluated, how they reduce to values. And this would make it very difficult to cheat and introduce side effects into your functions, because in order to use side effects, you have to be able to reason about when they're going to happen with respect to one another. And purity of functions is more or less required to deal with a lazy evaluation model. So another thing about Haskell that's different from, say, Clojure or Scheme is that there's a static type system. I won't say that static typing is better than dynamic typing or whatever, but when it comes down to it, in order to evaluate to a value, the data involved in your function has to make sense for the function that it's being evaluated with. And the point of a static type system is to make sure that that happens as early as possible. You still have safety in a dynamic language because it checks at the last minute to make sure that the values that you're trying to evaluate make sense. But a static type system, on the other hand, assigns types to the terms of your language as you're writing it out in the text, rather than just assigning types to the values right as they're being evaluated. And so it can check at compile time that everything makes sense. So everything in Haskell has a type, and that's the set of values that belong to that type. Functions are also values, and so they have function types. So different type systems are available for various languages. And I'm sure everybody's familiar with the Java type system, or the C or C++ type system. They are on the primitive end of type systems, especially as they were originally created. Java has got some more advanced features recently, but Haskell definitely is on the more advanced side, which means that it gives you a different set of properties about your program that are checked at compile time. And you can take advantage of these types and the type checking of the compiler to help you write your programs. A lot of people view a type system as as something they have to fight against to get their program to compile. And, you know, to some extent that's true. You've got to satisfy the type checker before the program will run. But most of the programs that you wrote that had those type errors weren't going to work correctly anyway. Maybe some of them would have, but most of the time, if your compiler is complaining at you because of the type error, you really did make a mistake, and you got to figure it out sooner or later. Anyway, it just makes sure that the properties that the type checker can check are satisfied before it even tries to run it. And the guy who developed some of the ideas behind modern type systems like those in Haskell and Scala has this famous quote. It says, "Well-typed programs can't go wrong." It doesn't mean that your program won't do wrong things, but it does mean that it's not going to get stuck in its evaluation somewhere because you passed an integer to a function that expected a Boolean value or something. Your evaluator is going to continue evaluating. So now I'm going to walk through this little function, and I know it's not a very interesting function, but in Haskell I think this kind of illustrates some of the important concepts in the language. First of all, let me explain the syntax a little bit. You can define types separately from functions. This is a type definition, and this is the corresponding definition of, it's actually a list of integers. So this isn't actually a function, it's a list. Here we have a function. You can see that this one is a function because it has an arrow there in the type signature. It's a function that takes an int as input and it outputs an integer. So that might seem a little odd, but an integer is the multi-precision arithmetic version. They're as big as you would like, and it won't overflow on you. Whereas an int is a machine-appropriate fixed-width integer. Okay. We have an interesting thing right here. This is an operator. They're user-defined. So you could write an implementation for that operator. And what this means is list index. So, and when you put, normally with an operator, you're going to have two operands on either side of it. But here we've created what they call a section. And basically, it's a function that takes one parameter, and when it gets that parameter, it fills it in on the right-hand side. And you can take either a right or a left-hand section of a binary operator. And Haskell is full of these little syntactic niceties that make it a little bit more complicated to learn, but they can be pretty handy when you're writing programs. So here we have some more operators. These are the list constructor operators. And here we have another operator. This one's in parentheses without any parameters to it. That means you can use an operator in parentheses like you would any other function. It just you no longer have to put it in infix position. Now it's just a function. So here we're passing the function plus to another function zipwidth. And here's the interesting part about this definition here, is it's self-referential, and it's not self-referential inside of a function. This is a top-level data definition. In most languages, if you were to write a top-level language definition, when the compiler compiles it, it will try and evaluate it right away. And if you have a self-referential data structure at the top level, and especially one that doesn't have a basis case well, you're not going to terminate. But that doesn't happen in Haskell because of lazy evaluation. Okay, so of course the point here is to calculate the Fibonacci numbers, and based on what you know about them, it's probably, you can guess at what this zip width function is doing. But basically, it's saying take the list of Fibonacci numbers and the list of the tail of the Fibonacci numbers. So fibs, of course, starts with this one, and tail fibs just chops off head, and you're left with the rest of it. So we've got two lists here that we're zipping together. And zip width is a higher order function that takes an operator, a binary operator, and two lists. And it just pairs up each element of the list and performs the binary operation on those pairs, creating a new list. So it's basically saying the Fibonacci sequences. The Fibonacci sequence starts with 1, 1, and then you sum the head of the list with the rest of the list pairwise with the plus operator from that point on. And this little equation here gives us the entire Fibonacci sequence. Of course, if you evaluate the whole thing, it will go on forever. But the point of lazy evaluation is it doesn't do that. So here, this is, like I said, is the index of operation. So we take the infinite list of Fibonacci numbers and take the nth one. So if anybody has any questions about anything, if anything's unclear, let me know. Go ahead.
So why do you have params around the plus operator?
That is to make it act like just a function. An operator normally occurs between two expressions.
Okay.
And in order to pass it as a parameter or to use it in prefix notation, you have to put parentheses around it.
So to be clear, plus is not a function like it is in Racket, where it's just used as any other function.
It's
Plus is an operator which is slightly separate than just a...
It's syntactically different.
Right, that's what I meant.
But operationally, it's a function. You define function or operators like any other function, except it just so happens that anything with a non-alphabetic character in the beginning is treated as an operator.
Okay.
Instead.
But it's the normal plus. I can say 1 plus 1, and it'll say 2. You know, it's,
yes.
It's the addition operator.
I feel like they're
Yes.
pretty similar because, like, you can
Yeah.
use any function as infix if you just give it like
Yes.
right.
Yes, that's the dual notion to turning an infix operator into a prefix function is that you can take any prefix function, so any named function with the standard alphabetic starting name, and you can put it in backticks and stick it in infix position. And so you can use any function as a binary operator. Yeah.
What kind of advantages does the Haskell type system offer over like the C type system?
Well, it's got a lot more machinery in it to deal with abstraction. C does not offer any abstraction at all in its type system. The types are just there to tell you how big something is, and to make sure that you don't, write a smaller value into a bigger one or a bigger one into a smaller one. It's mainly keeping track of the size of things. Whereas Haskell's types capture more semantic value of your problems. And I'll talk a bit more about the type system in a bit, but I am going to run out of time unless I move on. So I'm going to walk through really quick how evaluating fib4 works. So at the very beginning, you've got the definition fibs, and it's unevaluated. It hasn't been touched at all. It's just sort of sitting there, waiting. And here we are applying the value 4 to the function fib. And we substitute the definition, and we get fibs index at 4. At this point in an applicative order language, you would have infinite recursion because it would try and evaluate the entire fibs parameter before it called the index function. And you can't evaluate an entire infinite list in finite time. So here's a simplified definition of what the index function looks like. And this is another of the interesting things of Haskell, is that it's functions are defined as a series of equations. See, we've got two separate lines that both mention a single definition that applies in a certain case. And what we have going on right here is called pattern matching. We are basically supplying the data constructors here for a list, informing the compiler that we want to destruct the list instead of construct it, and bind some variables to what we find there. So this pattern here only matches when the n value is 0. So right now it's 4, so it's not going to match that one. It's going to match this one instead. The underscore means that we don't care about that value. We're not going to use it. It doesn't need to bind it to a variable. And this one names the variable that we want to be bound to the tail of that list, because you use this this operator to construct a list from a head and a tail, and this pattern matching expression here pulls it apart. And pattern matching here is there are two dual notions in Haskell that define how your program runs. There's constructing of data, and then there's a case analysis of data on the other hand. So constructing data builds stuff, case analysis tears it down, and case analysis is at the lowest level the only thing that forces evaluation. So nothing is evaluated until it is pattern matched in a function definition like this, or in a case expression. So anyway, this says that we need to evaluate this so we can do this pattern matching. Anyway, so we're not going to use this definition because the 0 doesn't match. So we'll have to use this one. And this basically says that it indexes on n-1, passing the tail of the list. So it should be clear how you translate this into your favorite functional languages recursive notation. This is our base case here with n equals 0, and this one reduces our problem size. And here's the definition of the zip width function, at least the part of the definition we're concerned with. Okay. So, like I said, case analysis forces evaluation, but it only does it to the next lambda expression or data constructor. It stops there until something else is demanded of it. So, like I said, this is going to force pulling the head off of the list. And so we're going to have to evaluate fibs far enough to get to this first data constructor. And then we have some bindings due to the pattern matching. So x's is some unevaluated thing, n is 4, and the head, which we're not really binding, I just listed there to make it clearer, is 1. And so n-1 is 3. So I think I deleted the slides. Anyway, anyway, we've got to do the zip width eventually. Oh no, it was okay. We had to take the other one that was just literally there. We didn't have to evaluate anything else yet. But now we've finished uncovering the constants that were there, and now we're left with this expression that's not just a constant value. You can't look at that and just say, oh, the head of zip width plus fibs, tail fibs is 2. You have to evaluate this first to find that out.
Just to be clear, the ones weren't in principle evaluated either, right? Since you weren't using
Right, they were constants. They were stuck there, and you pulled them out. You had to evaluate this cons here.
but not the one.
But yeah, the one, it was a 1. You couldn't evaluate that any further. So anyway, we're walking through this index function, and now we hit this other expression, and we've got to reduce it a bit first to before we can evaluate the other one anymore. So we expand this definition. See, we're breaking up these lists in each position into the head and the tail, and we're applying the function that was passed in to the heads of both lists, and then we're returning the list with that at the head, and then the zip with F and the tails. And this is what that looks like when you've expanded the definition. And see, we're trying to match up this pattern with fibs. So we've got to evaluate that before we can match it. This is what forces evaluation in Haskell. And it's the key thing to understand when you're programming in Haskell, because if you don't understand what makes evaluation happen, you can get into some troublesome situations. Okay, anyway, we've got to evaluate fibs and tail fibs so that we can perform these pattern matches. And we end up with, basically, we use this definition of fibs right here, which we've partially evaluated so far, and we just sort of copy the full thing here and the tail of it there. And they're references to the same data structure. So we're evaluating the list right behind where we're building it. So the evaluation follows this pattern where your outside function is demanding values through its pattern matches, and the inside function is building the list that you're trying to traverse with the outside function. And they start happening in lockstep once they catch up to one another. They sort of jump back and forth in the evaluation. So here we substitute the values that we got in here, and we substitute plus for F. And there we've got our next value in the sequence. Anyway, I hope the way that works is clear to everybody right now. Okay? We essentially have 2 coroutines that are working over the same piece of data. One is building it, and the other one's consuming it at the same time.
But still, yeah. The 2 is not going to be computed. It'll be a thunk that eventually would do 1 and 1 plus 1 if you ever needed that.
Right, and we did need this. We needed it to do this indexing operation.
Yeah. No, you needed the colon, you didn't need the value 2.
Oh, right. That's right.
That's what I mean to draw out. It really is lazy. And if you're not even going to use that first thing, you won't get a value.
Yeah.
Although if you need a later value in the array, wouldn't it then compute that too?
Well,
so it would compute the later things?
It would.
Yeah, you can
when you
move
hit
on
plus.
through the list.
Right.
But if you don't necessarily have to do anything with the nodes on the list,
The plus
and they'll just sit there as unevaluated expressions until you need the value. You have to actually do a case analysis on the value itself rather than just the list structure. So I cheated in this this diagram, and it was more strict than Haskell will be, and that was a good catch. Thanks for that. Anyway, we get to the end. We finally evaluated. It will evaluate this one because we've asked for it. The top level of Haskell, when you in the interactive interpreter run an expression, it will print out the last value and it has to evaluate it to print it. So that will eventually cause 5 to be calculated. Anyway, we're left with a sequence of expressions that will reduce to these numbers. And the fib4 evaluated to 5, or an expression that would reduce to 5 anyway. And if we were to make calls to fib again in the range that we went through, it wouldn't have to construct any more of this. It's already there. So we've defined a lazy memoizing Fibonacci sequence with a simple expression built on a list structure. And you can do this in other languages, but it requires a lot more machinery to build in the laziness that's required to do it. Whereas it's part of Haskell natively to work with data structures. There we go. Okay, when is my time up?
7:20, so
Okay.
15 minutes.
Okay. Advantages of laziness. So, if any order of evaluation that you can do on your program will reduce to a solution, lazy evaluation will reduce to that solution. Strict evaluation, on the other hand, will sometimes go off into the weeds and go into infinite recursion on functions that a lazy evaluation model would terminate on. On the other hand, there are still some expressions in Haskell that will go off into the weeds. But if any way of evaluating it would reduce to a value, the lazy model will. So the Haskell style of programming in these little composable pieces, sometimes if you were to use those kinds of pieces in a strictly evaluated language, your programs would run off into the weeds. And so in strict functional languages, you end up writing explicitly recursive functions a lot more often than you do in Haskell. You occasionally will write a recursive function in Haskell, but much more often you'll use a higher level function and not do recursion explicitly. So, like I said earlier, laziness is necessary, at least in some amount, to do efficient functional data structures, which is essentially what we were doing with this Fibonacci sequence. It was a data structure containing the entire sequence, but we only evaluated as much of it as we needed to. And you can use this to great efficiency in other functional data structures. So it does have costs. I'm not going to pretend that laziness is a cure-all. There's lots of people that would like the next Haskell to not be lazy, because it's not obvious when any particular piece of code will evaluate. Side effects would be intractable to reason about, so you just can't have them. Managing unevaluated expressions has both space and time cost. And even though I was sitting there thinking about that problem, I missed some of the laziness in it. And that's really easy to do, even if you're somewhat experienced at Haskell programming. You can forget that something is really building up a big expression, and you could think that you're passing along a value from like a worker thread, that you expected it to be calculating something, but really it's just built up a big expression, and you want your worker thread to calculate it, but it hasn't. It returns the value to you unevaluated, and so you haven't actually passed it on to a worker thread. So there's lots of little things like that that can catch you up if you're not expecting it. If you turn on higher levels of optimization, the compiler will analyze and try and figure out whether it's okay to be strict, because strictness is generally more efficient. And so, if you're lucky, the compiler will take care of that for you. But if you're not stuff can blow up unexpectedly. It's not impossible to deal with, and you kind of have to get into bigger programs before it becomes an issue, but it's an issue to watch out for. But laziness, purity, and a fancy type system, it kind of defines what Haskell is, that sets it apart from other languages. It's the only functional language that I'm aware of that's in common use that does lazy evaluation by default. And because of that lazy evaluation, Haskell has had to remain pure. And as Simon Peyton Jones, who's one of the lead developers of the main Haskell compiler, compared this forced laziness, or the forced purity, as the hair shirt of functional programming. This is sort of a religious thing to kind of show that you were, not concerned about worldly things, to wear a really itchy, scratchy, pokey kind of shirt. And it's kind of what purity did to Haskell programmers. They had to figure out interesting ways to deal with purity, because ultimately you have to interact with the outside world. So I'm going to skim through data types because I'm almost out of time. Data types in Haskell are built on the idea of algebraic types. And this is a lot deeper of a subject than I can go into right now, but it means that types are built out of more primitive types, and they can be built in two ways. They can be built by pairing types, basically a tuple. You have a value that can be any one of its set of values, along with another value that can be any one of its set of values. In set terms, that it's a pair is the Cartesian product of the constituent sets, and then the other that is what we have right here with our list type. We have a pair here that's either that's a cons A, or it's an A and a list of A. So there are two things there in this alternative. And the fact that we have an alternative here, it can be this or this. That's a disjoint union of sets. And it's sometimes called a sum type. And it basically says you can have one of these or one of these in your type. And you can kind of add on to those. So it's not just one or another one. You can have one of these or one of these, just a big enumeration. So enumerated types are sum types, and pairs and triples and whatnot are product types. And this gives you the flexibility you need to define pretty much any kind of data structure that you would like. Okay, so here's a little thing about how you can take the derivatives of data types to find the type of the one whole context of the data, which is a fascinating thing, and it would have been fun to talk about. But anyway, polymorphism. Haskell is parametrically polymorphic. And what that means is that in type signatures, you can have type variables. When you have a type variable, it has a sort of implicit universal quantification. For all A, this type describes the type of the function or value. That means that it has to, the function has to operate uniformly over all elements of the types that it can receive. So for any possible type that comes in, it has to do the same thing. So that means the function can't examine or otherwise poke at the values that it's passed if it's polymorphic in that value. There's no type case. There's no type of operator, and that places severe constraints on the authors of functions, because there's only a limited set of functions that make sense for a given function signature. For example, here's this type signature here. We have a function f. You can tell it's a function because of the arrow. It is from type A to type A. So, can anybody tell me what that function tells us about f?
Returns the same type that it receives.
Exactly. How many functions can take a value of any type whatsoever and return a value of that same type?
Well,
Two. I would say almost, well,
infinite.
yeah, I would say infinite. We could have the +1 function and then the +2 function and then the
But how can you add something? You don't know what it is. This could be anything.
Well, you can make a list of them.
It returns the
I
same
mean,
thing.
it doesn't return a list of A.
That's true.
It just returns A.
So it's the identity function dealing with
Exactly. There is one function, one sensible function anyway, that satisfies the signature. That is the identity function. And that's what is behind the idea of parametric reasoning. There are some interesting papers on what they call free theorems that arise from parametric polymorphism. They constrain the actual interpretations of, or the actual functions that can inhabit types. And that can actually help you as a programmer to figure out what functions do when you see their type signature. You think, what could this possibly do with the values it's getting? And this is a function, it takes as a parameter a function from any type A to a Boolean. It also takes an input list of A, and it returns a list of A. So this tells us that the elements of this output, the only place they can come from is this input. You can't create some arbitrary value, a value of an arbitrary type, that is, out of nothing. You had to get it from somewhere. Which elements from this list, which order they're in, and how many of them, they can only be determined by f in combination with this function. And the decision procedure to figure out how to figure out what goes in here can only inspect the length of this list and apply this function to its elements. So who has a guess for what one of the functions that satisfies this signature is?
Filters.
Exactly. And you can tell that just by looking at the type signature. They actually tell you a lot about what the function does. But this is only true because it's a pure functional language. You don't get to do arbitrary things behind the scenes.
So, sorry to go back to the identity function type signature. So if you define its type as that, but then you implemented it as something like, to the increment operator, the compiler would complain and say that type wasn't accurate?
Yeah,
okay.
It'll say that's a type error.
Okay.
Okay, this is one of the things you can prove with an actual formal proof. Well, not formal, but you know what I mean. It basically says that you can map over an element or over a sequence before you filter, or you can do it after you filter. It means exactly the same thing. And if you think about it, you can get a pretty good efficiency increase if you know that this holds, and you can do that transformation in your program. Okay, so type classes are another one of the big things that sets Haskell apart. Very few other languages have type classes.
A couple more minutes.
Okay. What type do we give the plus function? Well, we could say it's a function between integers, but then what about floating point values? We have to use another operator for floating point values if we've used integers for the normal plus. And we can't just say a to a because of parametricity. This could be anything that we're passing the plus, and you can't add something you don't know what it is. So we have a way to put bounds on polymorphism. We have basically a predicate says something must satisfy this predicate in order to implement this function. So for all types A, for which num A holds, we take an A and another A and return an A as a result. So this constrains these A's to be numeric types, and then we can say that we can add any numeric type. So we satisfy with that constraint by providing a unique instance at a class at a specific type. So we say that an integer is an instance of num, float is an instance of num, and then this dot 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 would be filled in with the specific things that you can do with a num, the ways in which your function is allowed to behave non-uniformly. One way to view type classes is as an extra parameter that to your function through which you get the correct implementations for the type involved. So your compiler would figure out that you were using floating point values or integer values, and it would supply a dictionary of the correct implementations of the functions for that type. But unlike object-oriented dispatch, this is dispatched based on type, not on the value itself. And your constrained type variable can occur at any position in the signature. It can be the return value, and that's used quite a bit.
So that's not any different from standard like Java dispatch.
But it is though.
But you said it's not dispatched on value, it's dispatched on type.
But it is dispatched on the value. It's the type of the value at runtime. It has an associated vtable that gets looked up.
Oh, okay.
Whereas this, at compile time, the compiler decides that it's going to pass.
So you may have a more generic type container for some value, but then when you actually pass that as a function, then
the function is completely generic, but it's provided the dictionary that it needs to operate on the bounds of its polymorphism. If that makes any sense. So these are the type classes that are implemented in the standard library. You can convert things to strings, read them back, compare for equality, types that have a total ordering, types that can be sequentially enumerated, types that have upper and lower bounds, numeric types that it doesn't give you all the numeric operations, that it gives you the ring operations. We have a whole numeric tower kind of like schemes, but not exactly. And then we have these warm fuzzy types, functor, monad, and monad plus. I'm not going to get into those with much detail because I'm out of time. But the compiler will derive show through bounded for you if you ask it to. I think I am out of time. I would have talked about some of the libraries that you get. We have monadic parsing combinators, which are a pretty clever use of Haskell. This is sort of an embedded domain-specific language that lets you create a recursive descent parser that looks pretty much like your BNF syntax does. This is a CSV file parser. There's a binary parser, software transactional memory. We've got JSON serialization. We've got efficient streaming libraries. There's the lens framework, which is generalized getters and setters. Lets you do some pretty fancy stuff that would be fun to talk about another time. There's the compiler itself, build tools, documentation tools. There's an online repository of everybody else's packages called Hackage. You can download things automatically, and all of the documentation is up there on Hackage. It's automatically generated from your source files. There's a benchmark tool that does some fancy statistical analysis and makes sure that you aren't being too lazy with your evaluations to measure what you want to. There's test frameworks. There's the quick check and small check testers that let you do automatically derived testing of invariance on your algorithms. So you can state some properties that should hold on your functions and test to make sure that they do over a random input set for quick check, or sort of an exhaustive analysis of small values for small check. And that's all I have. Hopefully I have piqued your interest in Haskell and given you an idea of what's interesting about Haskell with respect to other languages. Let me know afterwards, and I will be happy to point you to resources to learn more about any particular aspect of what I've talked about. Thank you.